Okay, welcome everyone. I'll just say at the outset, we are recording today's session. And so if you prefer to turn your camera off, please do so. We understand, but I'm sure Stuart would also like to see some friendly faces to talk to. There's also the option of turning on the live transcription via the CC button at the bottom of your Zoom toolbar. So I'd like to start today by acknowledging the Aboriginal and Torres Strait Islander people as traditional owners of the unceded land on which we work and learn. We pay respect to the elders past and present and the place of Indigenous knowledge in the Academy. I'd also like to acknowledge the people of the Wurundjeri Bullock tribe, who are the traditional custodians of the land on which I live and where I'm working from today, from home. So good afternoon. My name's Andrew Siebel. I'm the Platform Manager for Melbourne Data Analytics Platform, or MDAP. For those who are not familiar with MDAP, we're a diverse team of research data specialists who are working to enable data-intensive research across all of the disciplines at the University of Melbourne. We were formed as the workforce component of the Petascale Campus Initiative, now just called Petascale Campus. And this was a 5-year plan to accelerate the university's capacity for data-intensive research. And today we continue our MDAP seminar series by welcoming Professor Stuart Barr. Stuart is a director of the Australian Urban Research Infrastructure Network, or AURIN, and also Professor of Urban Data Science here at the University of Melbourne. Prior to joining AURIN in 2020, Stuart was Professor of Geospatial Systems Engineering at Newcastle University in the UK. Stuart's focus, particularly his research focus, is on the development and use of geospatial data, analytics and modelling for integrated urban infrastructure systems analysis. Today, he'll be talking to us about digitisation of the built environment and digital twins. So over to you, Stuart. Thank you.
Great, thanks, Andrew. So I'll just go through the first technical step today and share my screen and just ask anyone who's on camera if they can put a thumbs up that they can see it. Fantastic. So stage one complete. So many thanks for the invitation to come along and speak to you all today. What I want to try and do over the next 40 minutes or so is just give a pretty high-level overview of some of the work that I've been doing with colleagues back in the UK, but also out here in Australia, around the emergent capability now that's being developed, particularly in Australia, around the kind of built environment and digitisation of the built environment and the kind of umbrella that this has fallen under that we often refer to as urban digital twins. And in particular today, what I want to do is really outline some of the work I've done, but also to try and outline some of the challenges that we still face in actually delivering this kind of capability in relation to the built environment at scale, and consistently across multiple urban conurbations and cities in Australia. Just to slight pick up on the introduction that Andrew provided, I am still the director of AURIN here at the University of Melbourne, who are our lead agent, and also Professor of Urban Data Science. But just from the 1st of July, I'm actually moving back to the UK and will be going back to being Professor of Geospatial Systems Engineering. So if there's an interest at all in following up any of the content today prior to the 1st of July, please contact me at my University of Melbourne email. Post 1st of July, please feel free to contact me at Newcastle. So starting today's talk, if I can get the slides to progress. There we go. Across Australia at the moment, there's a significant move by individual states towards developing what is now, as I said, commonly become known as urban digital twins. Essentially, the ambition here is to develop full, comprehensive, spatially complete 3D representations of the built environment, the buildings, the infrastructure within them, the other assets that are located within the urban fabric, and to also be able to essentially monitor and understand the dynamics and the activities and the exchanges of demand and supply that's taking place within the built environment. And perhaps almost uniquely, because of the state-based system that Australia has, there's a real emergence of international leadership in Australia around these urban digital twins, as essentially each state is essentially trying to develop their own capability going forward. So, for example, in New South Wales, we have the New South Wales Urban Digital Twin initiative, which is essentially at the stage of almost having a complete three-dimensional city model of the whole of Sydney. We also have up in Queensland, the Brisbane Urban Digital Twin that's being developed, which is very similar, a 3D city model of the buildings and the infrastructure assets within Brisbane. And also equally within Victoria, where we have the Victorian digital twin that's been developed by the state government, and also initiatives such as the excellent work that's been done within infrastructure engineering here at the University of Melbourne with regards to the Fisherman's Bend Digital Twin Initiative as well. And so there's a really rich amount of work that's going on across Australia around building these digital representations, which are comprehensively, spatially extensive, and are trying to, as I said, capture the inherent sort of structure present within the built environment. However, one of the things which is still a challenge is that while we're able to develop and build these 3D city models and represent the sort of complex geometry of each of the buildings within the built environment, we're still on the kind of, if you like, the foothills of the Everest in terms of developing the required analytical functionality that allows us to drive new insights, new understanding from these digital representations of the built environment. And just to try and kind of put that a little bit in context, I thought it was interesting just to look at some of the very high level but international drivers around urban digital twin technology and development currently that is driving these sorts of initiatives. So, for example, on the left here, you can see the now almost infamous so-called Gemini Principles Pyramid, which was developed by the Centre for Digital Built Britain in the UK, that's based in Cambridge University. That was a result of a comprehensive consultation of academia, industry and government departments around what would be required to develop a national digital twin capability, essentially a sovereign capability around the built environment. And on the right-hand side, you can see a very similar piece of work that was undertaken by ANZLIC, the Australian New Zealand Land Information Council, around, again, the key components and aspects of what would be required within spatially enabled digital twins of the built environment. And both of these sort of high-level initiatives articulate quite clearly that while being able to represent and capture the data within the built environment, so that kind of bottom tier of the Gemini's pyramid you can see on the left-hand side, where we're looking around the data cleaning, the asset data, data structuring, and so on and so forth. But in actual fact, to deliver this kind of ubiquitous capability into the future, we need not only that data acquisition, but also the high-level analytics and simulation modeling capability that can leverage off that, and then a rich suite of decision support tools that help us improve our decision making and feed back from the digital world into the real world of the cities we live in terms of improved decisions and investment going forward. And in fact, within the Gemini's principles, it was clearly articulated, and this is something which is often forgotten, I think, in the work that I've seen going on globally, that there were two types of urban digital twins which were kind of recognised as being important. The first one, and one where I think we've seen the focus and the concentration of work to date, is around the so-called dynamic model of an asset, of a city, of a built-up area, where we're leveraging off real-time data of current performance and activity that's taking place via distributed sensors across the built environment, and looking to improve our situational awareness and decision-making in near or close to near real time, back into the system to make interventions as is appropriate. So this kind of concept of a real-time or near real-time digital twin capability for improved decision-making. However, there's also strongly articulated in Gemini's principles this concept of what's referred to as a strategic planning digital twin, essentially a digital twin which takes long-term conditional data on the built environment and the population, and basically looks to make long-term predictions around how we should make investments, interventions in relation to the longer-term planning over multi-decadal time horizons for the built environment. And we can think of this kind of strategic planning type of approach very much one which aligns well with the concept of building improved climate resilience, climate adaptation within the built environment going forward. So how do we actually decide when and how to make interventions over multi-year, multi-decadal time frameworks to make our built-up areas better to live in, more prosperous economically, more equitable socially into the future. And so we've still got this challenge, as I said, in terms of really genuinely developing operational at scale digital twins in both of these two types. I think we've made significant progress in digital twin type 1, the kind of near real time digital twin capability, and I'll touch on some of the work that I've done myself with colleagues in that space. And perhaps I would highlight that the digital twin 2, the long-term strategic planning digital twin, though, is a far more ambitious piece of work potentially, and one where we're seeing less activity globally at the moment, although I think that is likely to change into the future. So some of the challenges that we face in relation to the digitisation of the built environment, and key considerations in relation to those for the genuine development of digital twins at scale. The first one is actually something which isn't new. We've been talking about it for virtually the last 2 decades, and that's one around how do we handle the vast amounts of data which not only are being collected now in relation to the built environment, but also will be collected into the future. And traditionally, we've looked at the big data challenges around the built environment as being one very much based around data volume and how do we handle that at scale. That's probably less of an issue now with current modern data storage and database architectures. But what I think will become critical and key into the future in relation to the successful delivery of digital twins is how do we handle the velocity of data and the variety of speeds at which data is going to be delivered to us in relation to the built environment. We have a huge capability now around a rich suite of environmental sensing and IoT that's continually providing data in relation to our built up areas, but that's all coming at us at a variable velocity. So how do we manage that in a sensible way that we can provide the streaming services into digital twins that allow us to undertake the situational awareness and decision making in a timely manner. And the second aspect that I think is going to be important into the future is the sheer variety of data that we're going to have to be able to handle in a seamless and harmonized way for users into the future. We'll have data around our building stock and the characteristics of individual households. We have population characteristics, which are changing dynamically, but only tend to be captured within the kind of census periods in each nation. We have infrastructure, critical infrastructure networks, which are providing continuous flows and streams of services based on the demand of households and the populace within our built area. And then we have the very complex geometric models that are being developed to represent 3D cities and buildings, as well as building information models, which are being integrated increasingly into the digital twin and 3D city models that we're using within these environments. And then on top of that, we have a whole host of continuous monitoring through CCTV, traffic video feeds, etc., that we need to be able to account for. So we have this incredibly heterogeneous range of data types which are being fed into or will ultimately be being fed into our digital twins going forward. And traditionally, as I'm sure many of you are aware, most of the platforms we tend to try and work with try to apply a single database management system to try and fit all of these different types of heterogeneous data. And obviously the most popular has been over time the standard relational database management system. However, there is a real emergence and recognition now that we need to start to develop the database management systems which are appropriate for the different types of data that we're going to have to handle in relation to the built environment. And so we're now seeing the rich use of spatial databases such as PostGIS, the use of graph databases to represent infrastructure networks such as Neo4j, the increasing use of array-based databases for gridded and image-based data, so SciDB, and the best ever named database management system, Rasterman, are examples of this. And by doing this, we enable greater functionality according to the types of data that we're interested in handling. But obviously we now end up with a very heterogeneous database management, set of database management systems, which we need to integrate and bring together in some way to provide us with a single lens into the complexity of all this data. So in some of the work that I've been lucky enough to be involved in back in the UK, we've been starting to think about how do we start to build the hybrid and potentially into the future, the fully federated database management systems that allow us to interlink different database management systems which are based on representing, or the schemas are based on the best representation for the type of data that we're working with within this complex heterogeneous ecosystem of data. So in this particular piece of work, we've been building what's referred to as the National Infrastructure Modelling Database, NISMOD-DB. It's currently in a hybrid database management form, so it comprises of a suite of individual database management systems, some of which are standard relational for dealing with our traditional sort of tabular types of data. We have a spatial database architecture in there for dealing with essentially the three-dimensional building geometry and the spatial data assets. We are using Neo4j to represent infrastructure networks for example, electricity, gas, water supply, wastewater, and then array-based databases to represent hazard fields and things like rainfall instances across the built environment for looking at how hazards may impact the built environment within this hybrid approach. And so by building this sort of hybrid environment and then having a metadatabase architecture that sits on top of all these individual databases, we can actually start to do some quite interesting analysis in relation to the built environment, which would be incredibly difficult to try and do with a single traditional relational database management framework. And without the metadatabase architecture, would be impossible to answer because the requisite data would be distributed between multiple database systems which aren't actually linked or connected together in a sensible way. So what you can actually see here is one example of this. This is essentially on the right-hand side, a graph coloring representation of the electricity feeder network from every electricity substation in Newcastle upon Tyne in the UK. There's 742 of those for the Newcastle area. And these are the subnetworks that connect to every single property and building in Newcastle, of which there's 175,000 of those. Now our building footprint data and our substations data, our asset data assets, are held within two separate spatial databases in order to represent the geometry. For each of the buildings, we have a rich description around their characteristics. So we have information around their form, whether they're detached, semi-detached, terrace, an apartment block or a set of flats, or whether there's mixed land activity taking place. Equally, we have a number of models, which I don't have time to go into today, where we can essentially estimate the number of inhabitants or people who live in each particular property within each of the residential buildings in Newcastle. And so we've got this very rich description, ultimately, of which substation is servicing which building and the number of people who are dependent on electricity supply from a substation in a particular building. But we've got that represented within a number of different separate databases. So within NISMOD-DB, what we've done is essentially looked at how we can link and bring those databases together so that we can actually answer some quite complex queries which employ or require us to have nested queries across multiple databases to find out, for example, for a particular subnetwork of the electricity feeder network, how many people are dependent on that, how many households are dependent on that subnetwork. So here, the idea here is just to show that we can develop queries by nesting and combining the respective query languages of the different database management systems in a way to answer these questions around connectivity of infrastructure assets and services to individual buildings or households within the built environment. So by using the PostGIS spatial queries, combined with Cypher, which is the query language in Neo4j, we can extract out, for example, which subnetwork of the electricity feeder network is supplying how many households and the number of people who are actually dependent on that network going forward. And just to try and show the real potential of this, we've actually undertaken or built the entire feeder network for the whole of Greater London. So this is 17,000 substations connecting to over 3.5 million properties within the Greater London area. And again, this graph colouring you can see is each essentially a representation of each of the sub-feeder networks that actually exist for Greater London. And we've been doing a set of tests around how much more efficient our queries are by having this hybrid architecture. And so what you can see on the bottom graph is essentially a time improvement compared to trying to do a failure analysis of recognizing where there's been a failure on a network and then trying to recognize which substation is on that, supplies the electricity for that subnetwork that's failed, and then which properties are actually affected by that failure. And what you can essentially see is that compared to a standard relational database architecture, the orange block or colouring in the plot shows the hybrid solution in terms of getting more or less a 6 times improvement in speed in terms of being able to try and retrieve that failure location and the subsequent information about it across the whole of this very large complex infrastructure network representation. So by having this hybrid architecture, we actually gain significant improvement in terms of our retrieval of information and data around the built environment. So moving on, certainly I think we're going to see a lot more work over the coming years around the aspects of data management and dealing with this high degree of heterogeneity and variety of data that we're going to have to work with in relation to the built environment. And then, of course, we've got the challenge of, even if we can build the appropriate data management systems, how do we build and develop the systems that can actually leverage off that to provide us with the new insights and information we need to make improved decisions. And as I said, the Gemini's principles recognise 2 types of digital twins. And the first one being this real-time or near real-time capability. And the first thing I think that's important to recognise in this context is that in order to be able to develop improved analytics and models for near real-time decision-making, we need these distributed sensor networks and IoT systems across the built environment, which are providing us with these vast amounts of data around the current activity, movements that are taking place within the built environment. And so one of the things I've been involved with colleagues back at Newcastle University has been the establishment of what's called an urban observatory at Newcastle. It comprises of now over 3,600 sensors of different types, which are being deployed across Newcastle upon Tyne. It's been now running for the best part of 6 years. We have over 1 billion observations that have now been recorded in total. And we're using this urban observatory, this real-time sensor network and environmental monitoring capability to start to build what we call a 360 real-time capability, where we use the observations to parameterize and calibrate models and analytics in near real time. We take the outputs from those models and analytics, try to synthesize those to make improved decisions, and that then actually feeds back into the next iteration of improved observations and monitoring within the built environment, both spatially and temporally. And we're looking, the work we do at Newcastle is particularly based around looking at natural hazards. So for example, aspects around flooding, heat as well, and air quality, and looking at this approach across the key 3 dimensions of understanding the hazard, understanding the impact of that hazard, and then thinking how can we actually make improved decisions in real time. Just to give you, again, some context here, the work I'm going to show you very briefly that we've been doing is one that looks at utilizing a combination of real-time environmental weather stations, and there's 68 of those which have been distributed across Newcastle, along with transport and vehicle counting systems, of which there's quite a dense network, as there are in many cities now, across the entire city. And the piece of work I'm going to show you very briefly is one that's called Flood Prepared. It was a project that was funded by the Natural Environmental Research Council in the UK, which wanted to improve our ability to, in near real time, make a prediction around the impacts of extreme sudden convective rainstorm events across UK cities. And as many of you will know, as we've seen increasingly this particular summer in Australia, these convective rainstorm events are highly spatially variable, very temporally dynamic, and you can literally be getting up to 50 to 100 millimeters of rainfall at one location, and then yet several hundred meters away only, you could be absolutely bone dry within your urban area. So the problem we were trying to tackle is how do we improve warnings around these convective rainstorm events? How do we provide better adaptation and resilience to them in near real time? The work, or one of the primary reasons we actually undertook this work in relation at Newcastle, was we, back in 2012, there's quite a famous event for the UK. Doesn't really compare to the order of magnitude events that Australia's prone to around convective rainstorm flooding. But for the UK in 2012, there was a so-called Toon monsoon, where over a 90-minute time period, there was in excess of 120 millimeters of rainfall hit the centre of Newcastle. It caused widespread disruption. The whole of the metro line was brought to a halt. Mainline rail services were completely halted on the whole east coast of England. And the centre of Newcastle basically became unmovable. You couldn't route yourself through it, either driving and or actually walking. It was most of the centre was under at least 2 to 3 feet of water for 8 or 9 hours after the event. So what we're trying to do is, can we detect these types of events better ahead of time, and then can we put in appropriate adaptation? So the approach that we've taken in Flood Prepared is we're using very high range, high resolution weather radars, which are located, fortunately, on one of the university buildings at Newcastle. that we can utilize. We use that to parameterize and within a data simulation framework, a dynamic spatial temporal convective rainfall model. We then take that convective rainfall model and put that into a GPU accelerated hydrodynamic surface water flooding model. And then we use that surface water flooding model to tell us where we need to start monitoring for potential disruption and to look for things like how congestion's building up. And then we look to try and use that information around the congestion build-up to make a prediction around which parts of the road network are going to be knocked out by the flooding and or disrupted by reduced traffic flows or congestion into the future. So as I said, we're very fortunate in Newcastle that we have a high resolution weather radar that provides 3-minute interval, 30-kilometer radius rainfall measurements from Newcastle, so we can watch the emergence of these convective rainstorm cells. Colleagues in the Maths and Statistics Department in Newcastle have been developing the spatial temporal convective rainfall simulation model. And as I said, that uses data simulation to improve the prediction and reduce the uncertainty of the prediction during the simulation time. And then at an appropriate point in the process, that is then inputted into the hydrodynamic surface water flooding model. So far, we've been able to get this to a level of 15-minute time intervals in terms of the predictive capability. So that's allowing us essentially to get up to 45 minutes ahead of the actual rainfall event taking place in terms of our predictive capability of where we may expect there to be surface water occurring in terms of flooding. And one of the pleasing aspects of this work is that the hydrodynamic surface water flooding model, not only is it GPU accelerated to try and make sure that we can run it in an appropriate time framework, but it's of reduced complexity compared to many of the more advanced hydrodynamic surface water flood models. We've been validating it against the more complex models and also against some of the data which we've recorded from the 2012 event. And in fact, the reduced complexity model is performing very well in terms of estimating not only where you'll get surface water flooding, but the depth of that flooding, which is very encouraging. And then, as I said, we look to apply that to understand where in the road network we'll see road closures, because it's impossible to actually pass through the surface water that's been deposited, and or how free flow traffic speeds will be affected potentially, where you can still get through particular roads, but you'll have reduced speeds as a result of the amount of surface water that's actually present. And then using the CC video and traffic video data that's available from Newcastle City Council, like many people have been doing now, we've been developing TensorFlow convolution neural network approaches for undertaking traffic counts and understanding how that leads to congestion. Now, one of the things we have done in this project, but which is still ongoing, is we've actually managed to build a prototype workflow demonstrator that we can run permanently, which has actually hooked up all of these components, these separate models and analytics together to give us a complete start to end, albeit linear, workflow, which takes data feeds from Newcastle's Urban Observatory, the environmental sensor network that's distributed across Newcastle, feeds that in to the workflow, has a monitor that looks for triggering rainfall events from the weather radar. And then once those triggering events actually occur, we invoke the rainfall model, hydrodynamic surface water flooding model, and the impact assessment modules within the system. And we're looking to hopefully build on this work and deploy it permanently for Newcastle City Council at some point into the future. And as I said, we're looking at various options around how we can do that. So one option is that we have developed a very simple proof of concept real-time dashboard. So this is essentially, we recreated a synthetic data set of the 2012 rainfall event, and we've worked that through this workflow to show that we can actually couple the models together in a start-to-end system and provide the outputs on this dashboard, which is very simple, but at this stage at least allows us to understand where we're going to expect to see flooding and to try and validate that with the original data that was recorded from the 2012 floods. Looking forward, one of the potential future opportunities in this area is that back in the UK, there's a facility called DAFNI. This stands for the Data and Analytics Facility for National Infrastructure. It's very similar to ORAN in that it's one of the national research infrastructure facilities that's available to researchers in the UK who are working on cities and infrastructure systems. And we're discussing with the DAFNI facility how we may look to host the flood prepared capability on the platform, not just for Newcastle, but actually to be able to deploy it in the future for other cities across the UK as a generic capability. And as more cities and urban areas in the UK start to develop their own individual urban observatories, their environmental sensor networks going forward, that they can simply plug that in into an instance of the flood prepared workflow and capability on the DAFNI platform. So we think there's some real potential around how, by building these systems, we can actually do it at scale for different cities and urban areas into the future. And I'll just highlight a potential opportunity here in Australia in a similar guise. So at the moment, ORAN, the Australian Urban Research Infrastructure Network, we're currently developing our next research infrastructure investment plan, which will be going to the federal government with regards to our future funding for the next 5 to 10 years, although we're not entirely certain what the time horizon is at the moment because of the caretaker mode that the Department of Education have gone into with the election. But once we know that, one of the key activities that ORAN will be looking to try and help support into the future is how do we open up and enable researchers who are working within the built environment essentially to develop the new tools, the new analytics, the new models, which are going to develop these new near real-time capability around the built environment. And the model that we're working on is around one which, again, looks at a 360 solution, that we're not going to be around deploying the sensor technology and developing the IoT aspect. That's being developed by a large number of key big industrial players. It's also this environmental sensor networks are being deployed by the states within their own digital twin environments. But what we see Oran's role as one of providing an interface to those state-based digital twins and the IoT services through a set of streaming services, which then can be piped into essentially an analytics platform where Oran will support key state-of-the-art libraries and packages which are needed to help deliver the new set of tools and analytics and models for real and near real-time analysis and capability. So we would look to provide the most recent up-to-date TensorFlow, PyGAT for genetic algorithms, data simulation, software packages, so on and so forth, to provide researchers with essentially this platform for innovation around developing new tools and analytics. And then the most successful of those, and the ones which are considered to be of most appropriate use by the state-based digital twin capabilities, Oran would look to support into production level services to take them from research software actually into scalable services that can be deployed across multiple digital twins into the future. And so we see this kind of 360 model as being a key core component of the type of capability that we want to enable for researchers into the future. I was going to spend a little bit of time talking about the second type of digital twin, the strategic planning digital twin, but I'm just conscious of time. So I think what I'll do is I'll skip over my last few overheads I had on that and just move to maybe a final observation. That is around the top of the Gemini's Principles Pyramid that I showed earlier on. At the moment, I'm personally convinced we will solve the issues around the complexity and the variety of data that we have around the built environment. There is huge innovation taking place with regards to the analytics and the modeling and the simulation capability. And I think there will be emerging from research, and we're already seeing it, ultimately operational systems with regards to being able to make improved decisions in relation to the built environment. But however, I think the biggest challenge we face is actually how do we genuinely translate the outputs from those tools, from the analytics and the models, into a way that they can actually be used by decision makers to undertake the key decisions around improved investments or approved interventions, particularly around this near real-time requirement. And I think my colleague Mike Batty, who's one of the grandfathers of urban modelling and simulation from the UK, captured this really well in as far back as 2016, and that it's all well and good that we can develop models and tools, but actually how do we translate them into actionable and usable information into the future? And it's a real challenge. We have a really rich set of tools now available to us for visualization, for decision support. Many of those are enabling much better multi-objective perspectives and understanding around the built environment, allowing us to understand how the system is changing in real time, for example, multi-agent simulation and gaming technology being coupled together. But actually, how do we make that next step where these become actually operational capability that can be deployed? So I'll leave it with that challenge that I'm beginning to muse over myself personally, and just say thanks again for the invitation today. If there's any interest in engaging around this work, please don't hesitate to reach out to me, as I said, before the 1st of July here at Melbourne. And then from the 1st of July, I'll be back at Newcastle, but very happy to follow up for any questions or interest there is around this work.
Brilliant. Thank you, Stuart. That was a real tour de force of an amazing breadth of work. There are a couple of hands up here, not surprisingly from one of our colleagues, John in MDAP. So we'll go to John first and then Noel. Maybe we'll try and make the questions and answers relatively short so we can get a couple in. Thanks. Thanks, John.
Hi, Stuart. Thanks so much. And maybe just coming from a lot of us are users of Auron, and we thank you for doing all the hard work at Auron to provide data for us to work with. But I'm both an MDAPper and a river scientist, a fluvial geomorphologist. So I actually have a question about that reduced complexity hydraulic model. Is that something that's based on 2Flow? It's the only GPU model I know, or is that something homemade, so to speak? And what's the sort of, is it an open source thing that you are publishing, or?
Yeah, sure. So the model is actually one that was developed by colleagues at Newcastle University. The reduction in complexity is it ignores the subsurface sewer, essentially, dynamics that are involved in the flooding. So as you're probably aware that you can get a lot of hydraulic forcing from the sewer network, which actually can cause flooding to occur in places you wouldn't normally expect it to occur. So it completely ignores that. So it's essentially based around solving the equations just purely in terms of impervious surface material over the urban fabric, but ignores the urban drainage aspect of it. I would need to, I'm not entirely sure how far it's got towards being released as being open source or not, but I'd be very happy to follow up with colleagues at Newcastle on your behalf if there is an interest in that.
Yeah, definitely. I can see lots of applications.
Yeah.
Thanks, John. And Noel.
Hi, Stuart. Thanks for a great talk. This is a completely different question. It's more with, I suppose, regulation and guidance when new buildings are being built or retrofitted. Based on the information that you guys are needing, are there sort of government policies or new standards or guidelines to ensure that you don't lose data, or you actually get the data you need from these new buildings? So in theory, I can only really speak for the UK, because I haven't looked into this in particular detail for Australia. In the UK, there is now a requirement that every new non-residential building, there should be a full-blown BIM model available for it, and that needs to be registered with the appropriate planning authority within the local government office region that building's been constructed in. Now, actually getting hold of that is a different challenge, that you need to beg, borrow, and obviously not steal, on occasions. I think the bigger challenge beyond even that is that while we have a number of examples, and I would say that Fisherman's Bend is actually one of the best examples I've seen internationally outside of virtual Singapore, the ability to genuinely integrate the complexity of the building information models into the wider geospatial 3D city models is a real challenge. They use essentially different data formats and ways of formatting the data within
3D city models, we use CityGML, which is an internationally recognized standard from the Open Geospatial Consortium. For BIM, we use the Industrial Foundation classes, which is a completely different set of essentially schema. And there's been, over the last 10 years, I mean, I'm going to say dozens of projects, and I'm probably not too far off here, dozens of projects on trying to unify or come up with a unified schema between the two different formats. And we're still a long way away from being able to do it in a seamless way.
Oh, thank you, Stuart. Just looking at the time, people are starting to head off to their next commitment. So we might wrap things there. Just leaves me to thank you again for giving up your time and sharing with us. You know, what is a great. Yeah, I mean, Aura in itself is a great resource and untapped really in many ways. So something that I think we'll definitely follow up on. Our data specialists are always very keen to make use of these amazing databases and data sources. So thank you for that, and good luck with your move to Newcastle, back to Newcastle. And I'm sure you know, we'll be hopefully in touch and connecting with you or your research teams in future. So thanks everyone for attending. We've got another seminar next month, mid-June, so look out for that one. David Goodman from Faculty of Arts will be presenting, and then we'll have another in-person panel event around mid-July. So that's the next couple of things, the next cabs off the rank, and we'll look forward to seeing you all soon. So thanks again.
Thanks a lot.